All right, so now we're going to discuss how to extend Runge-Kutta methods to Lie groups. And so let's first set up a sort of a general class of equations. It's like on a Lie group. So let's consider a differential equation on a Lie group G, right, in the following form. So let's say that we have y prime of t is equal to a of ty y of t, right? T is greater than or equal to 0, and y at time 0 is on the group. Okay, so you want this to represent a flow which stays on the Lie group, okay, and you can guarantee that by having some constraints. It's like on what A is. So where A is a map from the rails, which is time, across the group to the Lie algebra. Okay. All right, and the claim is that any differential equation, it's like which evolves on the Lie group, right, has to be in this form. And the basic idea, of course, is that if the curve y of t is on the group, that means that y prime is in the tangent space. Well, this has to be in the tangent space. It's like at yt of the group, right? And you can always write a tangent vector at the point yt in this way, in the form of an algebra element multiplied by a group element, either to the left or to the right. So there is a convention, right? So this, of course, corresponds to the left or right trivializations of the tangent space to the group. Okay. So the remark is that any differential equation right, that evolves for y of t in G, right, can be expressed in this way. For a suitable choice of A, right? So you're not really losing anything. It's like by considering a differential equation, again, of this form here. All right? Okay, so what we're going to do then is that we're going to try to express the solution, it's like of this differential equation, at least for short time, in terms of the exponential, it's like of a Lie algebra element, of a curve in the Lie algebra, okay, multiplied onto the initial time. So let's say that, right? So for small time, t greater than or equal to 0, right, you can consider sort of solutions of the following form. Okay, y of t is the, say, the matrix exponential of some curve theta of t times the initial point y0. Okay, and so theta of t is in the Lie algebra, all right? And you can write down a differential equation which theta of t has to satisfy in order for the y of t, which you write down in this way, to be a solution of the original differential equation. Okay? Okay, so, and it satisfies the following equation. Okay, so let's write that down, right? So it looks like, let me just write it at the very bottom so that, or we can prove it. Okay, so it's theta prime of t is equal to the exponential inverse of at the point theta t applied to a t y. Okay, I guess we had sort of used a big Y here. Okay, so that's basically what's you're going to have to end up solving for. And so the idea, if you will, is that this observation allows you to rewrite the differential equation which lives on the Lie group in terms of a differential equation which lives on the Lie algebra. And of course, the Lie algebra is a vector space, and that, in principle, allows you to, to bring to bear, all the class of numerical integration methods which have been developed for vector spaces to this problem. And in particular, you can apply the Runge-Kutta method to this. So let me prove this result, and then we'll show how you could adapt Runge-Kutta to the solution of this equation, and then in particular, then how it relates to obtaining an approximation of the original differential equation. Okay, so let me write that. Maybe I should write this other equation down as well. Y prime of t is equal to a ty y of t, right? So those are the two main things it's like you should keep in mind. Okay. All right, so let me then prove this sort of result. It's like saying that you can write down a differential equation for theta by using this inverse of the sort of linearization of the exponential. Okay. All right, so let's prove that. Okay, so I first start with y of t equals to the exponential of theta of t times y0, and I can differentiate that with respect to t. Okay, so that gives you y prime of t is so the derivative of this, if you recall, it's like was right trivialized. It's like to give you this dx term, right? Okay, and this was really sort of the condition, if you will, that the derivative of this is this times exponential of theta h, right? So this being the derivative of that is really how you've chosen to trivialize. It's like this this term here. Okay, and then this is y0 is just a constant, so it's like you don't have to worry about it when you're doing the product rule. Okay, so you look at this, and then you see that this whole thing is, I guess there was another thing I should have written down, which was that y of t is the exponential of theta t applied to y0, right? So those are sort of the three things you want. You want to have the original differential equation, the differential equation for theta, and the equation which relates theta, it's like with y, right? Okay, so this thing tells you that this object here is just y of t. Okay, so the equation just looks like y prime of t is equal to dx sort of theta t, theta prime t times y of t. Okay, but you know that y prime is equal to a ty yt, so this is equal to a ty y of t. All right. So here you don't necessarily know that A is a full rank matrix, but if you want this equality to hold, of course it suffices if A is equal to this thing, right? So it may not be the only A which has that property, but certainly one of them is if A is given by this expression, then it's like this condition which you're looking for will certainly hold. Okay, so that's what we're going to do. We're going to say that A of ty is equal to dx theta t theta prime t. All right, and then of course we can take the inverse, right? So this tells me that theta prime of t is equal to dx theta t inverse a ty, right? Which is what we were trying to prove here. Okay, so that's the result we wanted to show. Okay, so we have sort of the pieces. It's like which we have what we want, right? Which is that we have the original differential equation on the Lie group. We have the differential equation which the Lie algebra element has to satisfy in order for this to be a solution of the original differential equation, right? So those are all the pieces we have in mind. So the claim is that once you have this, then you can construct a Runge-Kutta method from this, all right? And of course, it's like the first thing you want to do is you want to write down Runge-Kutta method for the theta terms and then do the reconstruction, okay? So let's see how you do that. And I guess I should have said that this equation has an initial condition, which is that theta at time 0 is just 0, okay? All right, so you know that normally the Runge-Kutta method, it's like looks like, you know, it's like the internal stage is equal to the initial value plus h times some weighted sum of the vector fields at the points, right? So the initial condition here is 0, so things are a little bit simplified. So let me just write down this theta sub k thing. And again, you should think of these as being the internal stage values of theta, right? Which is what we normally do. Okay, and so this is equal to, and then the initial value is 0, so that's 0. Okay, and then h times the sum from, say, L equals to 1 to nu of AKL, and then the vector field at internal stage value L, right? So, okay. And then the vector value is given by this. Okay. All right. So then you have that Fk is equal to the exp inverse theta k, right? Ak. All right. So that's applying this, and then you need to know what Ak is. All right. So Ak is just A at the point Tn plus ckh, right? So this is the time corresponding to the k initial stage, and then you need to know what y is at that time. So you need to know what yk is. So it's like the internal stage value for the group. It's like corresponding to this algebra element. And then of course the natural thing to do is to have yk be equal to the exponential of theta k y0, right? So here what would normally be yk would just be the exponential of theta k times y0. Right, but since it's a Runge-Kutta method, I'm just going to put it yn here because I'm thinking of going from the nth stage to the n plus, well, the nth value of the approximation to the n plus first value. Okay, all right. So that's sort of, you know, fairly consistent with what you expect. And again, the only thing it's like you have to evoke here is the fact that y is a function of t, is this exponential of theta applied to y0, and then so a natural candidate for what y at the kth stage would be is the exponential of theta k applied to yn, right? Okay, so those are sort of just the basic things, and then of course, you know, the other thing you want in the Runge-Kutta method is that you want to know what the value of theta is at the final time, right? So that's, I'm just going to call theta. Okay, so theta is equal to, again, the initial value is 0, so there's just the sum over L equals to 1 to nu of BL, right, and then F at L, right? So this is sort of fairly natural application of the Runge-Kutta method. It's like to this differential equation, again, only the caveat that you had to essentially evoke this to write yk in this form in terms of theta k. Okay, so, and then the last thing you have to do, of course, is to use the fact that, again, it's like y at the final times the exponential of theta at that time times y0. So, so you have that yn plus 1 is the exponential, say the matrix exponential. Maybe I should put matrix exponentials here, right, of theta k, well, no, not theta k, theta, right? applied to yn. So this whole thing, right, then is a method which takes you from value yn to yn plus 1, where both of these things are on the Lie group, right? And you guarantee that you're on the Lie group by virtue of the fact that the matrix exponential maps Lie algebra elements to Lie group elements, and that the group is closed under matrix multiplication, right? So if theta is a Lie algebra element, which you've constructed it to be, then when you take its matrix exponential, you get a Lie group element. This is also a Lie group element, and the product of it is a Lie group element. So you're guaranteed that yn plus 1 stays on the Lie group because of that. So this thing is called the Runge-Kutta Munter-Kaas method. So this is the Runge-Kutta Munter-Kaas method. So Munter-Kaas here refers to a single person. It refers to Hans Munter-Kaas, who's at the University of Bergen. It's like in Norway, all right? And one remark, of course, is that if you look at this, right, most of this is fairly straightforward. There's sort of two things it's like you want to be able to do efficiently, one of which is you need to be able to compute the matrix exponential efficiently. And the other thing you need to do is to compute this dx inverse, it's like operator efficiently. And so that's another piece of the puzzle, if you will. But at least at a formal level, it's like this makes perfectly reasonable sense. So let me just remark that to make this practical, right, we need efficient methods for computing sort of dx theta, let's see, theta k inverse applied to ak. All right, so so what's going to happen really is that there are going to be sort of series expansions one has to consider. And the other thing it's like one could do in principle is that, you know, you could replace the matrix exponential with, say, the Cayley map or sort of the other diagonal Padilla approximants if you're on one of these quadratic matrix Lie groups, right? And then you can ask, well, you know, instead of the dx inverse, you can maybe try to compute something like the d Cayley inverse maps, right? So so that's something it's like one has to consider.